Traditional architecture diagrams often look like a series of clean boxes in a void, but systems do not operate in a vacuum. The moment a design leaves the whiteboard, it collides with reality, and that neat logic shatters against external forces. To manage this collision, ISO IEC IEEE 42010-2022 reclassified the subject of architecture. The standard moved focus from a system of interest to an entity of interest, or EOI. This terminology change allows architecture to govern entire organizations, data structures, and systems of systems, rather than being restricted to isolated software packages. Every entity of interest exists within an environment, a specific intersection of business, legal, adversarial, and political forces acting directly upon the design. Under this standard, an architecture description serves as a formal proof, documenting exactly how these conflicting environmental forces are addressed within the design. The ISO 42010 framework provides a standardized ontology to decode this environmental chaos. This framework is built upon 4 pillars: stakeholders, concerns, perspectives, and aspects. Organizing a system through these 4 categories allows teams to manage immense volumes of requirements without succumbing to cognitive overload. The process begins with the first pillar, stakeholders. The architect must identify every person or organization with leverage over the system. If these specific roles and claims aren't defined at the outset, the resulting technical solution risks solving the wrong problems entirely. Clause 3.17 of the standard defines a stakeholder as any role, class, or organization that holds a right, claim, or interest in the entity. Traditional engineering often overlooks this, focusing only on direct end users and the developers building the code. This ignores the indirect ecosystem. Regulatory bodies and certification agencies may never touch the system's interface, but their authority dictates the right to operate. When data sovereignty laws mandate that user information cannot leave a specific country, a regulatory stakeholder is forcing a hard boundary onto the architecture's topology. Modern design requires identifying the extended adversarial ecosystem. Hackers, state actors, and market competitors are absolutely mandatory stakeholders in this framework. This photograph shows a nuclear power plant, a critical industrial control system where adversarial and regulatory stakeholders dictate the entire structure. Here, security cannot be an afterthought. It is a foundational requirement for the network's physical and logical separation. Omitting an indirect or adversarial stakeholder creates an architectural defect that typically only reveals itself during a production failure. After identifying the stakeholders, the architect must extract their concerns. Clause 3.10 defines these as the underlying what and why behind the system's existence. Concerns go beyond basic functional requirements. They encompass attributes like cyber resilience, system agility, and potential lifecycle risks. Mapping creates a many-to-many paradox. A CIO may demand low costs but maximum resilience. Conversely, system availability is shared globally. Users need workflow, owners protect revenue, maintainers avoid emergencies. Separating them prevents cascading failures. The standard implements this through Viewpoints, a specification framing related concerns. A viewpoint acts as a cognitive filter, allowing teams to focus on one area while intentionally ignoring irrelevant details. This creates manageable views, like data flow or deployment. A complete architecture description is the result of synthesizing these separated, highly focused viewpoints into a unified whole. As viewpoints multiply over time, it becomes easy to confuse how we look at a system with the actual properties it possesses. ISO 42010 uses a dual classification system to organize these perspectives and keep the documentation structured. This grid plots viewpoints onto 2 axes. The x-axis holds subjective perspectives, like a financial filter for cost. The y-axis holds objective aspects, like physical structural properties. Clarity emerges here. A data protection viewpoint forms, where a regulator's perspective meets an informational aspect. Using this intersection allows architects to manage complex environments without sacrificing the system's structural integrity. This entire structural framework supports a single objective: architectural traceability and rationale. The framework enforces rigorous logic. Every technical decision must trace back through a viewpoint to a specific stakeholder concern. Features mapping to no validated concern are overengineering and should be removed. Furthermore, if a verified concern lacks a corresponding feature, the design is incomplete. Documenting this rationale prevents architectural decay, ensuring the original design intent survives as teams change and environments evolve. Effective system architecture provides the formal evidence that the human conflict and environmental friction surrounding an entity have been structurally resolved.